So this week we're going to be talking about electrical circuits, simple machines, work, and mechanical advantage. So we're going to start with talking about the sources of electrical energy. You guys learned last week that electrical energy comes from the flow of electrons. So there's lots of different places where we get electrical energy from. It comes from hydroelectric, which is water powered. A lot of times you'll see they'll hook turbines and stuff up to like waterfalls, and that will turn the turbine and that will create hydroelectric energy. The Hoover Dam is a perfect example of a place where we get hydroelectric energy from. Wind power, obviously, we've talked about that a little bit. We were talking about green energy last week. That's with the windmills that turn, and they turn the turbine, which then creates electrical energy. We also have solar power that we get from the sun, nuclear energy that we get energy from the atoms of, or energy from the nucleus of an atom, and then of course we have chemical energy, which comes from batteries, and it is transferred into electrical energy. So lots of different sources where we can get electrical energy from. So once we have electrical energy needs a path to flow on. It doesn't just come through the air. It needs to have a path that the electrons can flow on. So we are going to be talking about series and parallel circuits. And a circuit is a closed path through which electrons can flow. Okay, the key word here is that the path needs to be closed. Okay, if it's open, no electricity will flow. Just like if you turn your lights off, that opens the path, the lights go off if you turn the switch off. Okay, and we're going to talk a lot more about that. We're going to talk about circuit components. What are the things that make up a circuit? And I think you need to fill these in on your video notes. If you see this, it's just a straight line that indicates that it's a wire. This is a resistor, and a resistor is anything that you plug in, any load that is taking or using electricity. So it could be your cell phone if you have your cell phone plugged in, or your hair dryer, or your alarm clock. Any of those things, anything that you plug in is taking some resistance. It's a load that is being taken, electricity that's being used on the circuit. Okay, this one specifically is a light bulb. Okay, this indicates a cell. We're not going to worry too much about that one, but basically, like, where is your electricity coming from? This indicates that there is a battery on the circuit, so something that is battery powered, and you're not always going to have a battery because a lot of the stuff that we use every day, think about in your house or at school, not everything is battery powered. Most things have a cell, and that's where electricity comes from. And then the last one is a switch, and so this would indicate that the circuit is open. You can see how there's a blank space right there, so that would indicate that the switch is open, but this is the symbol for a switch when you are drawing circuits. Okay, so AC or DC, and I'm not talking about the band, but alternating current and direct current. So when electricity was first discovered, and the first electrical station was set up, the electricity flowed to different places through direct current. And it was great because they figured out how to use electricity and have lights, but it was bad because people who lived in rural areas could not get electricity because direct current can only travel very short distances. So only those people who lived right around the electrical power plant would be able to get electricity back in the day. Okay, with direct current, electrons travel in one direction, and today when we're talking about direct current, we are mostly talking about the electricity that we get from batteries. Okay, everything else in your house and at school runs on alternating current. Okay, the good thing about alternating current is that it can travel long distances, so it no longer matters if you live close to a power plant or not. That electricity can travel long distances. The electrons switch directions. They go forward and backwards. That's why it's called alternating current. And it's the electricity that we get from power lines. Anything you have to plug in, okay, is alternating current. So remember that direct current is electricity we get from batteries, and alternating current is anything that we plug in at home or at school. Okay? going to talk about series circuits first because they're the easiest. A series circuit is a current travels in a single path from negative to positive. Electrons always flow from negative to positive. Okay, let me get all this up and then we'll talk about it a little bit. Too far. All right, so again, current travels from negative to positive. So our current is traveling from here around to here. Okay, and you see we have two resistors or three things that are plugged in on this circuit. Okay, with a series circuit, if you have one break in the path of the circuit, meaning you open a switch or a wire gets cut or something, then it's going to stop the flow of the current. Okay, so if there's a break in the line right here, whatever is plugged in here, here, and here is all getting turned off. The current is the same throughout the circuit. Lights are of equal brightness. Even if each one of these is, like, say this is a 20-watt bulb, this is a 50-watt bulb, this is a 60-watt bulb, if the total amount of current going through there is 60 total, then each one is getting 20 watts. It doesn't matter that this is a 60 watt and this one's 60, this one's 50, this one's 20. If there's only 60 watts of electricity going through that circuit, then they're each getting 20 watts. Doesn't matter what the wattage of the bulb is, they're only going to get 20. That's where that equal brightness part comes in. Okay, it says lights are of equal brightness. And a really good example of something that's wired in series are Christmas lights. You know, if one of those bulbs goes out, the rest of them go out. Okay, all right, let's move on. Let's look at some different series circuits. Again, series means single, okay, so one path. So we're going from our energy source, we're going to this bulb, this bulb, this bulb, and back to our energy source. Okay, remember I told you that electrons flow from negative to positive, so you can see the arrows here indicating that. So we're going from the negative end of our battery, we're lighting up our light bulb, and to the positive end. And this is the direction in which electricity is flowing. Okay, there's just one single path. Same here, negative, one light bulb, two light bulbs, but there's just one loop, one path. And same again, we're going from the negative end of the battery to these three lights. There's a switch here, it's closed, so our electricity continues to flow to the positive end. And again, we are moving in this direction from negative to positive. Okay, series circuits, one path. That's what you need to know. Okay, parallel circuits. Parallel circuits are a little bit different. If you think parallel lines, you're thinking two lines that do not touch each other, but we'll talk about those in a minute. So parallel circuits, current travels in multiple paths from negative to positive. So we're traveling in the same direction from negative to positive. However, the difference between parallel and series is that one break does not stop the flow of electricity. Okay, your current varies in different branches. Your current is going to go take the path of least resistance. A bigger light would be dimmer, but that's because each device receives the total voltage. So before, in a series circuit, it had to be shared, but in a parallel circuit, everybody receives this, the total. So if the total is 60, in a series circuit, each one would get, if there was three lights, they would each get 20. But in a parallel circuit, if the total is 60, then lights 1, 2, and 3 are all getting 60 watts. Okay? And there's no change when lights are added. Remember, when we add stuff to a series circuit, it's going to get dimmer. It doesn't work that way for a parallel circuit. Everybody gets the total voltage. Okay, so here's some examples. Parallel circuits have more than one path. Okay? So let's look at this first one. So we're going to go from negative to positive. So here's the first path, okay? And if something happens to that first light bulb and the light goes out, we can still go from our source, and here's our second path, okay? So there's a path to each individual light, and because there's a path to each individual light, if one goes out, the other one's still going to stay on. Okay, so if we look at our battery, here's our first path. And here's our second path. So it would actually go like this and then around. Okay, it's not this one. If this light goes off, the other one will still stay on. Okay, so that's the biggest difference. If you look down here, this shows a series and a parallel. This one is wired in series, so there's just one path. Okay, but this one down here is wired in parallel, so you have 3 paths. Here's your first path, second path, third path. Okay? Household circuits are a combination of parallel circuits. Too many devices can cause wires to overheat, so we have some safety features in place, like a fuse. They're kind of old school. They're with a fuse, the metal melts, which makes the circuit break and causes everything to turn off. But today we have what's called a circuit breaker. And the circuit breaker, we call it flipping the switch. So if your circuit breaker trips, meaning that it's too hot, there's too many devices on it, it's going to cause that switch to turn off, which will turn all of the stuff off until you reduce the load. You can turn it back on. So the fuses are old school. Probably not many of your houses have those. Most of them now probably have circuit breakers. Okay, moving on. From electricity to simple machines. So this is going to be a quick review. You guys have done simple machines. We're going to review them quickly and talk about how they affect efficiency and mechanical advantage. So first off, why were simple machines invented? They were invented by ancient people to help them overcome resistive forces and allow them to do the desired work against these forces. Think about some of the amazing things that ancient people did, like build the pyramids. Okay, they couldn't have done that without simple machines like ramps. Okay, all right, let's talk about them. A simple machine is a device that helps make work easier. Okay, it doesn't change the amount of work that you're doing, but it helps make work easier by doing one of these 4 things. So they can transfer a force from one place to another, change the direction of a force, increase the magnitude of a force, or increase the distance or speed of a force. And doing those 4 things helps make work easier. The 6 simple machines that we're going to talk about are the lever, wheel and axle, pulley, inclined plane, wedge, screw, and the other one that we'll talk about a little bit, but we're not going to include in our notes, is a gear. So a lever is a rigid bar that rotates around a fixed point called a fulcrum. The bar may be either straight or curved. In use, a lever has both an effort or applied force and a load. Okay, so when we're talking about a lever, there's going to be 3 parts. Think of it as a seesaw. This part is the fulcrum. That's where it pivots. And then you would have a load and a resistance force. So in this case, if it's a seesaw and you and your friend are on the seesaw, yay, okay, one of you is going to be the load and one's the resistance. So it depends on who's up and who's down, and it will switch back and forth. But one is going to be the load, one's going to be the resistance force. Okay, and we will be talking about those some more in just a second. Lots of different types of levers. So all of these are types of levers. I just talked to you about the seesaw. We have a rake and an axe. Okay, when you are talking about things that you hold, like a paintbrush, a rake, an axe, your wrist becomes the fulcrum because that is where the pivot point is. Okay, or your elbow, depending on what it is. Okay, so when you're using those things like a paintbrush, think about how you paint. Your wrist is your pivot point. Okay, so that would be your fulcrum. The next one is wheel and axle. The wheel and axle is a simple machine consisting of a large wheel rigidly secured to a smaller wheel or shaft called an axle. When either the wheel or axle turns, the other part also turns. So that means with a wheel and axle, guys, this entire thing is all connected together. So when the wheel turns, this entire part right here turns. This wheel is turning at the same rate as this wheel because they are connected. Okay? So wheelbarrow, motorcycle, a car, anything that has a wheel and axle. Okay? Pulleys. A pulley consists of a grooved wheel that turns freely in a frame called a block. So we have a couple different kinds of pulleys. I know you guys are familiar with them, but we have a simple pulley, which is a fixed pulley, meaning that this part is fixed to something or attached to something like the ceiling or a tree limb or something above. It is not moving. It is in a fixed location. Then you have a movable pulley where the rope is secured to something above, and then the pulley, the movable pulley, is attached to the load. Okay, and that helps to change the direction of the force. Okay, and then if you want to really get fancy and use something that will really help you to change the direction of the load and also decrease the amount of force you need to lift your load, you're going to use a compound pulley, which is a fixed and a movable pulley together. Okay? Inclined plane, we see these everywhere. An even sloping surface. The inclined plane makes it easier to move a weight from a lower to a higher elevation. Okay? A ramp and a doorstop are examples of an inclined plane. Stairs are examples of an inclined plane. Okay? Next, take a look at this. If you want less force to be applied, you're going to go over a longer distance. So if you're looking at these three examples, they are all moving, and I'm in drawing mode, so it just stopped moving. Let me get out of drawing mode. Okay, so if you take a look at the very first one, letter A, look at the force that's required to push that car up to the same height ramp. So our force is 9.8 newtons, but the displacement, or how far that car is moving, ends up being 0.9 meters. Okay? I'm going to pause it at the top. Alright, so now that it's paused at the top, they're exactly going up the same height, but as you can see, the displacement or the length for each one gets shorter and shorter. So because it's shorter and shorter, the force that is required becomes more for each of them, because this is a steeper hill. So you're going to have to push harder to get that car up that ramp. Okay, so when it says displacement, that means the distance from where you started to where you ended. So this right here, from here to here, is your displacement. So our force, as we get steeper, our force gets greater, but our displacement gets lower. Okay? But the last thing I want you to look at is the amount of work being done. The work being done is exactly the same in every scenario. Okay? So the steeper it is, the shorter your distance is, but the same amount of work that you're doing. Okay? Moving on. Inclined plane. So think about roads going up a mountain and stuff. Those are inclined planes, and they help us get up the mountain easier without using as much gas. But because it's an inclined plane, it's going to take longer. That's what we were just talking about with the amount of work that's being done. So the displacement is going to be further. Okay? Okay, so like I was saying, the same technique is used today in modern freeways, which travel winding paths through steep mountain passes. Okay, and that again is to reduce the amount of force needed to get to the same place, but it's going to be the same amount of work. A wedge. A wedge is a modification of the inclined plane. It's basically two inclined planes back to back. So here's an inclined plane, and then here's the second inclined plane, and they go together, and that makes a wedge. And a screw is also a modified version of an inclined plane. You basically have, you basically have a cylinder. Trying to get my drawing mode on. There we go. You basically have a cylinder, and then you take an inclined plane and you wrap it around this, and that's how you get the screw. I think there's a better example over here. Yeah. So you can see here's the cylinder and the inclined plane, and then it gets wrapped around, and the different as it wraps around, that creates the threads. So your drill bits, your jar lids, all of those things, an actual screw, all of those are examples of how a screw is used. And that's it for simple machines. We're going to go on to a mechanical advantage of a simple machine. So mechanical advantage is how many times more force you get out of a simple machine. Simple machines increase your mechanical advantage, and that is the most important thing that you need to know. Simple machines increase the mechanical advantage. So a mechanical advantage of 6 means the machine outputs 6 times more force. So that means you put 10 newtons of force in, you use some kind of simple machine, and you get 60 newtons of force out. Okay, so simple machines help you get more force. You don't have to put as much in. The machine helps you. You get more out. Easy as that. Efficiency of a machine. So this is a little bit different than mechanical advantage. We're talking about how efficient a machine can be. So the input force times the distance equals the output force times the distance, or that formula is right here. No, you don't need to know it, just for our purposes right now. If we were to put some information in here, we would find out that some output force is lost due to friction, okay? Which means no machine has 100% efficiency. That is the most important thing that you need to know. No machine has 100% efficiency due to friction. So when we're talking about energy transfer and a machine is using energy, some of that energy is being transferred to heat energy or thermal energy. And because of that, no machine is 100% efficient. So to bring that into terms that you guys understand, we use things like if we're talking about a motor in a car, obviously there's moving parts and they're touching each other, and as soon as they're touching each other, remember you're going to have friction. Remember I had you guys wave your hands around in class to feel the friction between your hand and the air molecules. Okay, so as soon as you have those moving parts in a machine, like an engine in a car, you're going to have friction. So to reduce friction and increase efficiency, we add things like oil to our car so that it is lubricated and it moves. It's easier to have sliding friction between those parts. However, friction doesn't go away. Friction is everywhere. So there's still going to be friction there's still going to be friction, which creates thermal energy, which is why after you've run your car for a while, if you feel the hood of your car, you will feel the heat from the engine of the car. Okay, that is heat that is created due to friction, or that it's transferred to thermal energy. Okay, so no machine is 100% efficient. You're going to put in more than you get out as far as efficiency goes. Okay? And objective 75, I can describe work and identify if work is being done. When we're talking about work in a scientific sense, it's a little bit different. So work is done when a force acts on an object and the object moves. So you're going to have a force acting on it. Whoops. So a force is acting on an object, and the object has to move a certain distance in the direction that the force is applied. So you do need to know this. Work equals force times distance. There it is. And we measure work in joules, which is a Newton meter, a Newton times a meter. So remember, we did force equals mass times acceleration, and our unit for that was a Newton. So now work is force times distance, so we're going to do newtons times meter, and that is going to give us a joule. Okay? So if we look at our first example, how much work is being done by a weightlifter below that applies 500 newtons of force, lifting a mass of 2.5 meters. So work equals force times distance. Our force is 500 newtons. Our distance is 2.5 meters. So we get 1,250 joules. Okay, simple as that. Work equals force times distance. Okay, so here it is. That's exactly what I just went over. Okay, how much work is being done by a weightlifter that applies 1,000 newtons of force but does not move the mass? If we use our formula, work equals force times distance, our force is 1,000 newtons, whoops, extra zero there, times 0 meters, work equals 0. So guess what? If he isn't moving that, no work is being done. Okay, so he's just holding it there. It's not moving a distance. No work is being done. Okay, so remember that for work to be done, you have to apply a force and it has to move. Okay, so let's think about these. And you tell me if you think work is being done or not. Okay, according to the scientific definition, what is work and what is not? Is a teacher lecturing to her class? Is a force being applied, and is it moving a distance? What do you think? How about a mouse pushing a piece of cheese with its nose across the floor? Is a force being applied, and is it moving? Is the object moving in the direction of the force? Okay, so the answer, I thought it was going to pop up, sorry. The teacher is not doing work, but the mouse is doing work. So let's talk about the mouse. The mouse is using a force to move the cheese a distance. The mouse is applying a force to the cheese with its nose, and the cheese is moving in the direction of the force. So because there's a direction and a force, we do have work being done. How about these? A scientist delivers a speech to an audience of his peers. Work or not work? A bodybuilder lifts 350 pounds above his head. A mother carries her baby from room to room. A father pushes a baby in a carriage, and a woman carries a 20-kilogram grocery bag to her car. Which one's work? Which one is not? Let's see. Scientist delivering a speech? Nope, not work. Bodybuilder lifting 350 pounds above his head? Yes. A mother carries her baby from room to room? No. Mom is moving a distance, but the force is being applied to the baby. The baby isn't moving a distance. The mom is moving a distance, so that is not work. A father pushing a baby in the carriage, yes, he's applying a force to the carriage, and the carriage is moving a distance. A woman carrying 20-kilogram grocery bag to her car, again, same thing as carrying the baby, that is not work. She's applying a force to the baby, but the baby isn't moving. Okay, mom is applying a force to her legs, and her legs are moving her body, so her walking is work, but her carrying the grocery bag to her car is not work. And that is it. I'm sorry these video notes were so long. Make sure you ask me any questions in class if you have them.